Okay, today we're going to cover Rolle's theorem. Rolle's theorem has three hypotheses. The first hypothesis is f is a continuous function on the closed interval AB. Second hypothesis, f is differentiable on the open interval AB. That means f has a derivative and it exists on the open interval AB. Third hypothesis is that f of a equals f of b. If these three are all true and satisfied, then there exists at least one number c in the interval AB at which f prime of c is equal to 0. And that's called Rolle's theorem. How does that work? Let's look at this pair of axes, and suppose you have a function where f of a is equal to f of b. So a would be here, b would be here. F of a equals f of b means f of a is at this red point, and then f of b is at this red point. If the function is continuous, it means when the graph goes from a to b, no matter what it does, because f of a is equal to f of b and the graph is continuous, it would have to come back. So if the graph goes down, it would have to come back at least once. It could do this more than once or just once. If it goes up, then at some point it has to come down. And the point at which it makes its trip down, this point is the point C, at which the derivative is equal to 0. So here, f prime of C is equal to 0. And C is between A and B. This means C belongs to the interval AB. So C is between A and B. If any of these is not satisfied, then we cannot apply Rolle's theorem. In this example 201, f of x equals x squared minus 6x plus 2 in the interval 1 through 5. And the question is asking, determine whether Rolle's theorem can be applied to the given function f in the closed interval AB. If it can be applied, then find the number c, that special number c, at which the derivative is equal to 0. So let's see. This is a polynomial function, so it is continuous on 1, 5. Closed. It's also differentiable. What that means is we can find a derivative. Its derivative is 2x minus 6. And let's calculate f of 1 and f of 5. F of 1 is obtained by substituting 1 for x. So it's 1 squared minus 6 times 1 plus 2, which is equal to minus 3. F of 5 is 5 squared minus 6 times 5 plus 2, which is equal to minus 3. So f of 1 and f of 5 are equal. Therefore, the third hypothesis is satisfied. So Rolle's theorem applies. And if it applies, we find the derivative and we set it equal to 0. Here's the derivative, 2x minus 6, set it equal to 0, 2x equals 6, x equals 3. So c is equal to 3, and 3 is in the interval 1 to 5. Let's do another example. Okay, 202, f of x equals square root of x minus 1 between 0 and 4. Well, let us check. If you substitute the lower limit, the left limit of this interval in for x here, you end up with square root of 0 minus 1, which is square root of minus 1. That is not defined. So f is not even defined. Therefore, it's not continuous. F is not defined at x equals 0. You could also have tried a half or anything less than 1 and it still would not be defined. And if it's not, it means it's not continuous, so there's no need to check anything else. The theorem does not apply to this situation. Same thing with example 203. In example 203, here f is not defined at x equals 2. So x cannot equal 2. 2 happens to be inside the interval. So therefore this function here is not continuous on the interval on 1, 3, because it is not continuous at one point in there. So therefore the theorem does not apply. Let's do another example. 204. F of x equals cubic root of x on the interval -2 to 2. Cubic root of x can be written as x to the power 1/3. Okay, x to the power 1/3 is a cubic root, so it's continuous even for negative numbers. It's continuous on the interval -2 to 2. For the differentiability, we need to differentiate it and see. The derivative of x to the power 1/3 is f prime of x equals 1/3 times x to the power 1/3 minus 1, which is 1/3 x to the power -2/3. This x to the power -2/3, we're gonna write it as 1/3 and then bring x to the -2/3 down to the denominator. X cannot be equal to 0. And because 0 is in this interval here between -2 and 2, the first hypothesis is satisfied, but the differentiability hypothesis, the second one, is not. So the theorem does not apply. Does not apply to this case. So we cannot find C. The next theorem we're going to cover is the mean value theorem. The mean value theorem has only two hypotheses. It has the continuity and the differentiability. So f must be continuous on the closed interval. F must be differentiable on the open interval. That's it. There's no third condition, no third hypothesis. If these two are true, then there exists at least one number c in the interval AB at which f prime of c is equal to f of b minus f of a over b minus a. If I were to draw a situation like this with small a and small b, and then this number here would be f of a, this number here would be f of b, and let's call those points capital A and capital B. So f of a is this red point here, f of b is this red point here. F of b minus f of a is the difference, this difference here, this distance, and that's called the rise. B minus a is the difference between these 2 points. It's called the run. Rise over run happens to be the slope of the segment AB. So this is telling us that there exists at least one point between A and B at which the slope of the tangent is exactly the slope of this segment. So if I were to join these, the slope of this segment here is equal to the slope of this tangent to the graph, and that point C happens to be here. Okay, so that's the mean value theorem, and we're going to do an example. Example 205. F of x equals x cubed in the interval 1 to 4. Well, first of all, x cubed is continuous on the interval 1 to 4. Closed. The derivative of x cubed is 3x squared. It is also differentiable. F of x is differentiable on the open interval 1 to 4. Okay, so therefore there exists a point C, a special point C. What we need to do is calculate f of 4 minus f of 1 over 4 minus 1. Here it is. It's actually f of b minus f of a over b minus a. A is 1 and b is 4. So it's f of 4 minus f of 1 over 4 minus 1. Okay. F of 4 minus f of 1 over 4 minus 1. F of 4 is 4 cubed. F of 1 is 1 cubed over 4 minus 1. This would be 64 minus 1 over 4 minus 1, which is 3. 63 over 3 is 21. So there exists a point at which the slope of the tangent is going to be 21. The slope of the segment is 21, so we need to look for the point at which the slope is 21. So what do? We set up f prime of c equal to that. F prime of c equal to the slope. Okay, the derivative of this is 3x squared. So 3x squared equals 21. X squared equals 7. So x equals plus root 7 or minus root 7. Minus root 7 is outside the interval 1 to 4. We don't want that. Plus root 7 is inside. So we reject the minus root and we keep the plus root. You only keep the root that's inside. So x equals root 7, that means our special point C is root 7. At that point, The slope is going to be 21. And 21 also happens to be the slope of the segment joining A and B. And this completes the lecture on Rolle's theorem and the mean value theorem.